Hi guys, welcome to our next lesson. This one is on integral exponents. Now we're going to be working with exponents that are a whole number integer. So this is what an integral exponent is. So let's do this by exploring some patterns in exponents. Let's start here on the left hand side looking at the pattern we have when we have decreasing exponents on a base of 10. So 10 to the power of 3 equals 1,000. I have an exponent of 3, I also get 3 zeros when I have a base of 10. 10 to the power of 2 is equal to 100. Again, exponent 2, 2 zeros if I have a base of 10. Same applies to the exponent of 1, so my answer there is 10. It's a bit different when I have a 10 to the power of 0. Remember, anything to the power of 0 is going to be equal to 1. But now I move down and I've got a negative exponent here, so what does that look like? And if I have something to the exponent negative, then that means I need to put it as a fraction where I have 1 over the base. And in this case, I have negative 1 as the answer. So it would be 1 over 10 to the exponent 1. 10 to the exponent negative 2 would be equal to 1 over 100. And I can write this as, with positive exponents, as 1 over 10 to the exponent 2, because 10 to the exponent 2 is 100. Let's look at the next one. I have 10 to the exponent negative 3. So this would become 1 over 1,000 because 10 to the exponent 3 is 1,000. And I can also write that as with a positive integer, because we like to write things with positive integers, as 1 over 10 to the 3. And so really we need to decide what pattern's happening here. Well, I went from 1,000 to 100, and what this is actually just repeated division. And it's repeated division by 10. So let's apply that same thing to our next pattern here. In this one, our repeated division is not by 10, but instead we're taking the answer that we have there. And what's happening here? Well, it's actually repeated division by 3. 3 to the exponent 3 is 27. 3 to the exponent 2 is 9. 3 to the exponent 1 would be 3. And now remember, we're doing repeated division here. We're dividing by 3 each case. So again, we can also look at this as 3 divided by 3 would equal 1, which corresponds to 3 to the exponent 0. That's going to equal 1. I can keep going down for my negative exponents. So 3 to the exponent negative 1 would give me 1 over 3. 3 to the exponent negative 2, I can write as 1 over 3 to the exponent 2, or I can write it as 1 over 9. Excellent. Let's look at another example. So we looked at it with some actual numbers. Now let's do a general example with a variable. So here I have a to the exponent 0. Remember that a to the exponent 0 is going to equal 1. And then I have a negative exponent here, a to the exponent negative 1. That's going to be 1 over a. A to the exponent negative 2 would be 1 over a to the exponent 2. So we want to try and write things using positive exponents. Let's look at these ones. Here I have 10 to the exponent negative 7. And to write it with a positive exponent, what I need to do is take the base and the exponent and put it all over 1. When I put it as 1 over 10 to the exponent 7, I'm changing it to a positive exponent. Let's look at another example. 3 to the exponent negative 5, writing with a positive exponent, would be 1 over 3 to the exponent 5. And if I look at a to the exponent negative n, well, then I can write that as 1 over a to the exponent n. All right, let's look at how we can use exponent laws to determine the negative exponent. So here we have a question that's 5 to the exponent 4 divided by 5 to the exponent 7. And what we need to remember here is our division exponent rule, which is that when we are dividing with exponents that have the same base, we subtract the exponents. So we can write this in expanded form. So we can write the repeated multiplication for the top and the repeated multiplication for the bottom. So then, after we have that done, what we need to do is cancel out what we have on the top and the bottom. So I can cancel out the 5s that I have the top and the bottom, and what I'm left with would be 1 over 5 to the exponent 3, because I have repeated multiplication of the 5 there 3 times. My final step for this question would be then to evaluate the bottom, giving me 1 over 125. We can also just apply our exponent law here, where we have 5 to the exponent 4 divided by 5 to the exponent 7, remembering we need to subtract the exponents to give me 5 to the exponent 4 minus 7. Again, we want to write this with a positive exponent, so I can turn this into 1 over 5 to the exponent 3 and evaluate it to be the same as 1 over 125. Now this brings us to our general rule. So what our general rule is that negative exponents in the numerator get moved to the denominator and they become positive. So we can write this as a to the exponent negative p equals 1 over a to the exponent p. So let's look at some examples. Let's write these as positive exponents and then evaluate them. For this first one, I have 2 to the exponent negative 1. That becomes 1 over 2 to the exponent 1, which would equal 1/2. All right, this next question, I have 3 to the exponent negative 2. So I can rewrite that as 1 over 3 to the exponent 2, and then evaluate the bottom portion, where I have 3 to the exponent 2, which would be 9. Okay, question here states 4 to the exponent negative 3. So we can rewrite that as 1 over 4 to the exponent 3, which is equal to 1 over 64. All right, so let's look at a slightly different example. What would happen if there was a negative in the denominator of the question? Well, that's kind of weird because our other rule was that we would have to put that as 1 over 4 to the exponent 3. So, that doesn't, what? Okay. To solve this, we're actually going to have to think about our rules for the division of fractions because we're going to need to rearrange this and then flip the second portion of it to multiply. So let's take a look at this. Remember that when we have a negative exponent, we want to write that as a positive exponent, where we put it as 1 over the 4 to the power 3. But we end up with this weird thing where you have 1 over 1 to the exponent 4 over 3. So what we need to do is actually apply our division rules for fractions, where we flip the second one and then multiply. So we end up with 1 times 4 over 3 over 1, which is just 1 times 4 over 3. And again, you end up with an answer there of 4 over 3. So that makes much more sense. And of course, 4 over 3 would be 64. And so that is your negative exponent law. When you have negative exponents in the denominator, they get moved to the numerator and then they become positives. But what you need to remember here is that you only move the negative exponents. We don't move positive exponents. And that'll become clear when we do some examples together. So your general rule here is that if I have 1 over a to the negative n, this just becomes a to the exponent n, a positive exponent. But a cannot equal 0 here because it's in the denominator and division by 0 isn't allowed. Okay, let's spend some time looking at some examples. So here we have some examples, and really what we need to do is apply our exponent rules. So in this first example, I have 4 to the exponent 5 times 4 to the exponent negative 3. So because I'm multiplying, that means I need to add the exponents. And I really need to remember my rules for operations with integers. So I would have 4 to the exponent of 5 plus a negative 3, which means that I would have 4 to the exponent 2, because 4 plus a negative 3 equals 2. My answer there would be 16. All right, let's look at the next question. Here I have 1 over 2 to the exponent negative 5. Now here's one of those tricky ones where we have that negative 5 or negative 5 exponent in the denominator. So we can apply the rule we just learned, where this means that it's 2 to the exponent 5, which would equal 32. All right, so here we have 2 to the exponent 3, and that's inside the brackets, and it's raised to the exponent negative 1. And remember, this is our product rule, so the power of a product rule. So really what we have to do here is we would have the base of 2 raised to the exponent negative 3, because it would be 3 times a negative 1. And because we are raised to a negative exponent, we rewrite it as 1 over 2 to the exponent 3, or 1/8. Okay, so for these questions, we want to decide if it's true or false. Does 8 to the exponent 3 over 8 to the exponent negative 1 equal 8 to the exponent 4? Well, let's look at it. Apply our exponent rules. 8 to the exponent 3 is being divided by 8 to the exponent negative 1. So that means I need to subtract the exponents. So I would have 8 to the exponent 3 minus a minus 1, which means that I would actually be adding there. So it would be 8 to the exponent 4. So, because one side equals 8 to the 4, that equals the other side, 8 to the exponent 4. So it's actually true. Okay, let's look at this next one. Over here on the right, I have 8 to the power 3 divided by 4 to the exponent negative 1. And we're saying that that's equal to 2 to the exponent 4. Now you might be tempted to try and see if you can apply some exponent rules here, but those exponent rules only work when the bases are the same. So we can't actually apply any exponent rules here. So in this case, 8 to the exponent 3 over 4 to the exponent 1, it doesn't equal to the exponent 4. This is false. Now in this case, they want us to see or want us to prove or state whether it's true or false that 2p to the exponent 3 does not equal 1 over 2p to the exponent 3. So let's take a look at that. So for this one, I have a negative 3 exponent, but that's actually only just being applied to the p. It's not being applied to the 2, only the p. So in actuality, what we have is 2p to the negative 3, it equals 2 times p to the exponent negative 3. So when we rewrite this, it actually looks like 2 times 1 over p to the exponent 3, which we can rewrite as 2 divided by p to the exponent 3. And that's not the same thing as what it has there on the right-hand side. On the right-hand side, it says 1 over 2p to the exponent 3. And this just is not the same. Okay, so let's keep rolling and look at some examples where we can apply these exponent laws. In this first one, we have a to the exponent 4 times a to the exponent negative 3. Now we're multiplying here, so we need to make sure that we apply our product rule. So we need to add our exponents. So I have negative 4 plus a negative 3. So we have to remember our integer operations. And this would make my answer here would be a to the exponent negative 7. And I know that I need to write a to the exponent negative 7 as 1 over a to the 7. In this next question, it's y to the exponent 6 divided by 2y to the exponent 5. So what I have there is a half actually, because there's this hidden 1 in front of that y to the exponent 6. So I can rewrite this as 1/2 times y to the exponent 6 minus a minus 5, because it's division that's happening here, so I need to subtract my exponents. 6 to subtract a negative 5 would give me y to the 11, so I'd have 1/2 times y to the 11. And I can simplify that as y to the 11 over 2. Either way would be correct. Here I have negative 2x to the exponent negative 3. And whenever I have a negative exponent, I need to take what it's being applied to and put that as a denominator in a fraction where we have 1 as the numerator. So this becomes 1 over negative 2x to the exponent 3. My next step here is to use my power of product rule and bring that into the inside of the brackets. And remember that that also applies to the coefficient. So I would have negative 2 to the exponent 3 and x to the exponent 3. Simplifying further, I would have 1 over negative 8 times x to the exponent 3. Okay, let's keep moving. In this question, we have 5p to the exponent negative 2, where the negative 2 is outside the brackets, and that's being divided by 5p to the exponent 4. Now, if I have this outside the brackets, that means that what I need to do is take what's on top, the numerator, and put it underneath the denominator with a positive exponent. So this becomes 5p to the exponent 2. But here's where that rule we talked about before comes into play. We don't move exponents that aren't negative, so this one stays on the bottom. And our answer there is 1 over 5p to the exponent 2 times 5q to the exponent 4. But we can simplify this further, because on the bottom, we can multiply our coefficients, giving us 25p to the exponent 2 times 5q to the exponent 4. And again, we can simplify further by taking 25 and multiplying that by 5 to give us 125 p squared and q to the exponent 4. Okay, but how does it work if we have a fraction that has, there's a fraction for a base and a negative exponent, like 2 over 3 to the exponent negative 4? Let's try this one together to check it out. So we need to consider and complete the following. If we have 2 over 3 the exponent 4, it becomes 1 over 2/3 the exponent 4. And this is where, again, we need to keep our multiplication and division of fractions. So if I have 1 over 16 over 81, what this actually is division of fractions. And when I'm dividing fractions, I need to actually multiply the reciprocal. So what would happen here would be that I'd have 1 being multiplied by 81 over 16. And that would just be 81 over 16. But if we flipped the second one and multiplied, what would happen if we just flipped our original fraction? So what would 3 over 2 to the exponent 4 be? Well, we could just bring in our exponent. We could have 3 to the exponent 4 divided by 2 to the exponent 4, which would actually give us the same answer of 81 over 16. So what that actually means is that 2 over 3 to the exponent negative 4 is actually equal to 3 over 2 to the exponent 4. So we don't have to perform that other math. We can just flip this one and do the positive integer. So this is a way that we could quickly evaluate other questions. So why don't we try it here? We have 5 over 2 to the exponent 3. If we flip the fraction and then apply a positive exponent that's the same, we would end up with the same answer. So in this case, we flipped it, and then we can apply the exponents. We have 2 to the exponent 3 divided by 5 to the exponent 3, so we end up with 8 over top of 125. So in general, we can say that a over b to the exponent n is equal to b over a to the exponent n. So thanks for watching, guys. Have a great night.